Section 13.4, Motion in Space, Velocity and Acceleration. First, suppose that I have some vector function r, parameterized with some parameter t, and we consider this parameter t to be time. Then we define the velocity vector and we denote it by the vector v, as just being the derivative of this position vector r. The speed, denoted by s, of t, will just be the norm of the velocity vector. Notice that the speed is not a vector. It's a scalar function. The acceleration vector, denoted by a, is the derivative of the velocity vector. Newton's second law of motion states that the force vector is equal to mass times the acceleration vector, assuming that the mass of your object is constant. Projectile motion. So suppose I have some sort of projectile, and it has initial velocity v0, and we launch it at some angle alpha, and the only thing acting on it is gravity. And we assume that gravity goes down with an acceleration of g. So we have that this travels along some sort of path. Okay. Then, at time t, its position will be parameterized as follows. X equals v0, and the only force acting, so once the projectile has been launched with a velocity of v0, no further forces act on it except for gravity, which is downward in the j direction. And so x, the position x here, is v0 cosine alpha t. Y is v0 sine alpha t minus the 1/2 gt squared, where a projectile is fired with angle of elevation alpha. Here's my angle of elevation alpha. Initial velocity v0, and the only force is gravity with a constant strength of g. So let's show this. Well, I know that force is equal to mass times acceleration. And so this downward force is just a negative, because it's downward, mg times j. And so I have that the mass times acceleration is equal to minus mg j. And so the acceleration is equal to minus g j. And so integrate, I get that the velocity is equal to minus GTJ plus some initial, well, plus some constant vector. Well, I know that initially the velocity so I know here that initially here, my velocity is V0. So that's initial. And so this is going to be V0 sine alpha, V0 cosine alpha. And so I have here that V0, that V at 0 is, and maybe I'll do it with components, V0 cosine alpha I plus V0 sine alpha J. Okay, so plugging in 0 here, I have that C is equal to, well, this. Oops. Sorry about that. It's equal to, and maybe I'll write it this way. Well, is equal to the above. Since at 0, this is 0. And so V is equal to, and maybe I'll write it in a more compact way. So this is V0 cosine alpha, and then V0 sine alpha minus GT. And so I can integrate this. So R prime is just equal to V. So if you integrate, maybe I'll just write this as R prime. And so if you integrate, this is going to equal V0 cosine alpha T. This will equal V0 sine alpha T. And, well, the integral T will give me a 1/2 GT squared plus C. In this case, is going to be the initial position, but I can assume that the initial position is 0. So this is plus, notice that when if you plug in 0, you get 0 here. So this is the initial position, but the initial position is 0. And so we get that R is V0 cosine alpha T V0 sine alpha T minus 1/2 GT squared. And that's what I wanted to show. So I'm done. The tangential and normal components of acceleration. So I can write the acceleration in the following frame, the tangential and normal frame. And so I can write a of t is equal to some scalar, a sub t, times the unit tangent vector, plus a sub n times this principal unit normal vector, where a sub t is just the derivative of the velocity vector. Where a sub t, maybe I should write this as, let me write, this is really s. So this is s prime, really. Let me write this as s prime. Where a sub t is equal to s prime, the tangential component of acceleration, and where a sub n is equal to the curvature k times speed squared, the normal component of acceleration, where the speed is just the magnitude of the velocity. So let's show that. Well, the velocity is just the speed times the unit tangent. So this here is s of t, and this, in parentheses, is the unit tangent vector. Okay. So the acceleration is equal to, well, the derivative of the velocity. So let's take the derivative of the first times the second plus the first times the derivative of the second. Let me write this as follows. And so this can be written as the norm of t times t prime over the norm of t prime. But this is the normal. Oh, and maybe, and this is just, oops. And this is the curvature times the norm of R prime, which is the curvature times S. So this is so the acceleration can be written as S prime of t. Good. S prime of t. I just wanted to check something. So S prime of t times so S prime times t plus, this will be S squared. But let's see, I want the curvature first. So this will be K of t, the kappa times S squared times the normal. And that's what I wanted to show. Okay. So, Kepler's. So, Kepler's laws of planetary motion are: a planet revolves around the sun in an elliptical orbit with the sun at one of the foci. Here we're assuming that this is just a two-body problem. In the universe, there exists the sun and there exists a planet revolving around the sun. So you assume that that there's one sun here, and this planet is going around the sun. So there's an orbit. It goes around the sun in some sort of periodic matter, periodic way, that it has some sort of keeps somehow revolving around the sun. So one, a planet revolves around the sun in elliptical orbit with the sun at one foci. Two, the line joining the sun to a planet sweeps out an equal area in equal times. Three, the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. So let's show this. So first, let's do the first one. So force is equal to mass times acceleration by Newton's second law. And by Newton's universal law of gravity, we have that the force of gravity is given by minus gm, which is the mass of one of the objects, let's say the sun, little m, the mass of the other object, let's say the planet, over r squared. Here are soon to be some sort of the length of this vector times a direction. So let's actually times some unit direction. So it would be r vector over the norm of r. So let's just multiply the r squared times the r to get r cubed. Next, let's look at the following cross product. R times V let's suppress. So all of So these are all functions of t. So I'm just suppressing the fact that these are functions of t. So let's take the derivative of this with respect to t. And so I get this is equal to r prime cross v plus r cross v prime. Just using the product rule or Leibniz rule, or well, the analogous Leibniz rule for the cross product, for the vector product. So this is equal to, well, r prime is just v, and v prime is a. But I know that v cross v is just 0. So this is 0. Anytime you cross a vector with itself. And I know that the acceleration, oh, I guess I should have said that. 1 second. So from here, the m's, since these are equal, then the m's cancel. And I have the acceleration is equal to this. So maybe I'll have to write that down here, that the acceleration is equal to minus gm over r cubed r. Okay, so this is equal to minus gm over r cubed times the vector r. And so I have that this is equal to r cross minus gm over r cubed r. So I can take this constant out in front by the properties gm over r cubed, since this is a scalar function, times the cross product r cross r. But as above, when you cross a vector with itself, you just get 0. And so this is equal to 0. Okay. So this says that the orbit of the planet is a plane curve. In the plane, orthogonal to, perpendicular to, the constant vector r cross v, since its derivative was 0. So let's do some notation. Let h be r cross v. And so in this case, this will be a constant vector. let U equal R over the norm of R, and let R equal the norm of R. So if I don't put a little vector on it, it means that it's a scalar. And so H is equal to R cross V and R is equal to U times R. So using this notation, I guess, I have that U equals R over R. So R is equal to RU. And so let's take the derivative of this. So by the Leibniz rule, the product rule, this is R prime U plus RU prime. So this is equal to R prime, again, by the properties of the cross product, I'll bring the R and R prime out in front, times U cross U, plus, this will be an R squared, U cross U prime. Well, I know that any vector cross itself is 0. And so I get that H is equal to R squared U cross U prime. So A cross H is equal to, well, A is minus GM over R cubed R. Let me write this as the R, vector R over R, let's write that as U. Cross H, which is R squared times U cross U. So this is equal to well, again, by the properties of the cross product, I can take the R squares cancel. So I get minus GM U cross U cross U prime. And by one of the properties of the cross product, the last one, where I can write the cross product as well, as these things involving the dot product. This is equal to a minus GM times U dot U prime U minus U dot U times U prime. So well, U dot U is 1. U dot U prime is 0. And so this is equal to a minus and minus, make that a plus GM U prime. Okay. So I have that V cross H, let's take the derivative of that. That's just V, again by the product rule. That's just V prime cross H plus V cross H prime. And so H is a constant, so this is 0. Anything cross 0 is 0. And so V prime is just A cross H. And so V cross H prime is G mu prime. And so integrating, I get V cross H is equal to, well, let's integrate this, GM U prime is equal to, well, GMU plus some constant vector. So let's do the following. Let's let H equal HK and C equals CI. Then R is equal to R cosine theta I plus R sine theta J. And so R dot C is equal to, well, if you dot these together, you just get R C cosine theta plus, well, this is going to be 0 times this other part, so plus 0. And so R dot V cross H is equal to R dot, well, what we had from above, G M U plus C. So this is R dot V cross H is equal to, again, by the properties of dot product, G M, these are just scalars, R dot U plus R dot C. And so I have R dot V cross H. Well, this is just G M R U. So R is just RU, but by properties of the dot product, I'll just write it as an R out here, but U dot U is 1. Plus R dot C, which is RC cosine theta. And so I have, this is equal to R dot V cross H equals GMR so GMR plus RC cosine theta. Okay. We also have that R dot V cross H is equal to R cross V dot H by the properties of the cross product, but R cross V is H. And so this is equal to just H squared. Oh, did I wait 1 second? So this is equal to where you make it into a I hope up here I stated that. let me just check something. Where h, yeah, where h is this. Okay, good, I did state that. Okay, so this is equal to so this is equal to h times k dot h k. And so this is h squared k dot k. But k dot k is 1. And so this is just h squared. Okay. So now let E equals C over GM, and let D equal h squared over C. And so h squared is CD, and GM is equal to C over E. So I have here that from the above here, that h squared is equal to GMR plus RC cosine theta. And so h squared is CD, GM, maybe I should put GM in parentheses, GM is C over E. Okay. And so I have CD equals C over E R plus RC cosine theta. I can cancel out the C's and multiply by E. So cancel out the C's. Maybe I'll do that like here. And then multiply by E. And so I get ED is equal to R plus RE cosine theta. And so R is equal to ED over 1 plus E cosine theta. Therefore, this says that the path, 1 second, get control back of the screen. What in the world? Okay, get control back of my screen. Okay, so the path of a planet? Well, so this says that it's it's some sort of conic section. Okay, but since we're assuming that a planet, by definition, has an orbit, then the conic sections, well, there's only one conic section, the ellipse, is a special case, the circle. And so the path of a planet is a conic section. With the focus at the origin, i.e. the sun, with, okay. And so assuming a closed orbit, this gives, it is an ellipse. And of course, one special case of an ellipse is a circle. So the only closed orbits, which are conic sections would be either a fixed point, and you assume that your planet is actually moving, a circle or an ellipse. And the circle is fine. It's just a special case of an ellipse. Okay, let me do part 2. So that finishes our part 1. So done with part 1. Let's do part 2. So H is equal to R cross R prime. So R cosine theta, R sine theta, cross R prime. So let's take the derivative of that. So it's the derivative of the first times the second plus the first times the derivative of the second. And then times the derivative of what's inside, theta prime. And this is the same thing for the y component. So derivative of the first times the second plus the first times the derivative of the second. Oh, I don't like dots because now they look like, okay. Since I'm dealing with dot products, I don't want to put a little dot there. And so just not to confuse you. Okay, so this is equal to so let's do the 1, 2, 3. So let's do this vector product, the cross product. So you do 1 first, so it's 2, 3. So 2. Oh, Oh, and of course, this is supposed to be a constant. Ooh, I should have written that there. And a 0. It's in the XY plane. So let me do that. Okay, so that's better. Okay, so it's 2, 3. So 2, 3. So, so R, so 0 times R sine theta minus, so that's 2, 3, 3, 2. So 1 times oh. Okay, 1 second. It's going to be 0 in that component. Okay, so, sorry. Okay, so 1 second. So, 2, 3, 3, 2. So 0 times R prime sine theta plus R cosine. So maybe R theta prime cosine theta. Don't need extra parentheses, comma. Okay, so now that was that. So next is 3, 1. So 3, 1. So 3 is 0. R prime cosine theta minus R theta prime sine theta minus 1, 3. So 1, 3 is 0 again. 0 R cosine theta. Okay, and then 1, 2. So 1, 2. So 1, 2. R prime sine theta plus R theta prime cosine theta minus 1, 2, 2, 1. So 2, 2. R sine theta 1. R prime cosine theta minus R theta prime sine theta. So this is equal to. So finally, a lot of things will cancel out and be nicer. So 0 minus 0 is 0. 0 minus 0 is 0. A lot of stuff. So R prime, R prime, cosine theta, sine theta, just multiplying the R, cosine theta inside the parentheses. R times R is R squared. Theta prime, cosine squared. Minus R prime, cosine theta, sine theta, minus and minus become a plus, r squared, theta prime, sine squared theta. Okay, so it'll become much shorter now. So h is equal to 0, 0. The r prime, cosine theta, sine theta, those cancel. So I just get r squared, theta prime, cosine squared plus sine squared, which of course is 1. And so I finally get h is equal to r squared d theta dt k. And so this says that r squared d theta dt is h. And since dA is 1/2 r squared d theta for a sector, for the area. So the area of a sector let me just maybe draw that. So I have for a little sector that dA is 1/2 r squared d theta. Then I have that dA dt is equal to r squared over 2 d theta dt. And so I have that dA dt is, well, r squared d theta dt is just h, so this is h over 2. And so this says that, well, it's constant. So dA dt is a constant. And that's what we wanted to show. Let's do the third part. Well, dA dt is h over 2. And so integrating, I get a is equal to 1/2 ht plus a constant. Well, this constant here is just going to be 0. You're assuming that when t is 0, the area swept out by a planet is 0. So we're parameterizing it where we say that we start when t equals 0. I'm measuring this. And so if I consider one whole orbit, call the time it takes to go around one orbit t, so that's the period, then this is equal to, well, pi ab, the area of a ellipse. And this is a year, or whatever you want to call it. This is time of it to complete one orbit. And of course, we call that a year. And so I have that, well, let's multiply both sides of my equation by 2 and square both sides of my equation. So h squared t squared is 4 pi squared a squared b squared. Well, h squared is gm b squared over a. And so I get that t squared is equal to 4 pi squared over gm times a cubed. So these are just constants. And so the period is indeed, the square of the period is indeed the cube. And so I've proven the third part. Okay, let's do some examples. On page 918, in problems 9 through 14, find the velocity, acceleration, and speed of a particle with a given position function. So r is t squared, comma, sine t minus t cosine t, comma, cosine t plus t sine t, and this is for t greater than or equal to 0. Okay, so let's take the first derivative, and then the second derivative to find the velocity and acceleration. And so, well, so let's take the first derivative. Derivative of t squared is 2t. Derivative of sine, cosine. Product rule, derivative of the first times the second minus plus the first times the derivative of the second. Take the derivative of cosine minus sine. Use the product rule for the second part. Derivative of the first times the second plus the first times the derivative of the second. So let me simplify this. So my velocity is equal to 2t. The cosines cancel, the sines cancel. So 2t, t sine t t cosine t. Let's find the speed. And so let's take the norm of velocity. So again, let's do the dot product. So the norm squared. So 2t squared plus t cosine t squared plus t oops, that's a sine t squared. Plus t cosine t squared. Get a little more room here. So the speed squared is 4t squared plus t squared. I can factor out a sine and cosine squared. I can factor out a t squared. So this is 1. And so uh, 4t squared plus 1t squared is 5t squared. So the speed is just t rad 5. I can assume that the time is greater than or equal to 0. So I don't need an absolute value. Now let's do the acceleration. Let's take the derivative of the velocity. And so the derivative of of 2t would be 2. The derivative of t sine t by the product rule, derivative of the first times the second plus the first times the derivative of the second. The derivative of t cosine t, derivative of the first, again, use the product rule, derivative of the first times the second plus the first times the derivative of the second. And so that's my acceleration. Okay. 26. A projectile is fired from a tank with initial velocity, fired from a tank with initial speed of 400 meters per second. So 400 meters per second. Find two angles of elevation that can be used to hit a target 3,000 meters away. Okay, so let's do that. Recall well, maybe I'll sort of draw it here. So you're shooting and so recall that x is equal to v0 cosine theta t, y is equal to v0 sine alpha t minus 1/2 gt squared. Okay, once, let's see if I can get control back. Minus 1/2 gt squared. Okay. And you want to figure out, you want to hit some sort of target that's some distance away. Okay, so we have here alpha and some initial velocity v0, and we want to go, let's say, and because I use this in the book, the distance is d. Okay. And so y is 0 when we hit the ground. Okay. And x is d. Okay. And so if y is 0, then it is either 0 or something else. Well, you assume that t is not 0. So let's assume that t is not 0 because that's initially when you fire the object. So that's not really a very interesting thing. So let's assume t is not 0. That would be very trivial sort of solution. So the one solution is not that I haven't actually shot the projectile yet. And so, for one thing, it won't be 300 meters away. So let's assume that t is not 0. And so in this case, t is equal to, I'm going to have to get some more room here. T is equal to 2 v0 sine alpha over g. Okay, so now, here, let me get a little more room here. Oh, I put it at the wrong location. Wait 1 second. Let me undo that. New page. For 1 second. I want the page here. Okay. Okay, come on. And let me get back my, okay, good. Okay, so D, the distance you have to travel. Trying to get control back, good. And so D, the distance you have to travel, is V0 cosine theta times t, which we said was 2 v0 sine alpha over g. And so I have a v0 squared over g. I have here a 2 sine alpha cosine alpha, so that's a sine of 2 alpha. Okay, so now we can do this problem. So it says assume that you are 3,000 meters and the initial velocity is 400. Okay, so let's do that. So the distance is 3,000. Initial velocity 400. Don't know angle yet. Sine of sine of 2 alpha. Oh, will you please stop? Okay, get me back control of my computer. Okay. Okay, all divided by g. Which is approximately 9.8. But let's not use that yet. And so, let's move this out the way for a second. Okay, good. So this is 3,000. G is 16. 160,000. Sine 2 alpha. So sine 2 alpha is, get rid of 3 of the zeros, 3g over 160. And so I have that alpha is equal to arc sine, 1/2 arc sine of 3g over 160, which you can plug into your calculator if you want, assuming that g is like 9.8. And, well, you have another angle. You can do pi over 2 minus this. So alpha equals pi over 2 minus 1/2 arc sine 3g over 160. And that is your answer. So these are the two angles. Okay. Good enough. Okay, so let me do problem number 40. In exercises 37 through 40, find the tangential and normal components of that. And so let's take the first and second derivatives. So this is equal to 1 2et 2e 2t. And let's take the second derivative. So this will be 0 2et 4e to the power 2t. Okay. Let's take the dot product of this. So R and maybe I'll press the T here. Dot R double prime is going to equal, well, 1 times 0 plus 2et times 2et plus 2e 2t 4e 2t. And so this is equal to this is going to be a 4 e2t. Let me factor out, so that'll be a 4e2t. And let's factor out a 4e2t from this. So it'll be a plus a 2e2t. Okay. And let's look at the square of the speed. So r prime squared. So the magnitude, the norm of r prime squared, is going to equal, well, 1 squared plus 2et quantity squared plus 2e2t quantity squared. So this is equal to one. Oh, but I can actually make this easier. So this is going to be a 1 plus 4 e2t plus 4 e4t. So this is a perfect square. So I can write this as 1 plus 2 e to the 2t squared. And of course, this is going to be greater than 0. So this is just 1 plus 2 e to the 2t. Okay, so the tangential component is just equal to, well, actually, let's do this first. Let's look at r prime cross r double prime. Okay, oops. Okay, so let's do that. And again, let's do the 1, 1, 2, 3. Okay, so this is equal to, so you do 2, 3. So 2, 3 is 2 e to the t that's a 4 e to the 2t minus 2e to the 2t, 2e to the t, and a 2e to the 2t. Okay. And then let's do, so that's 2, 3. Now do 3, 1. So let's do 3, 1. So that's 0. 2e to the 2t. Minus 1, 3. So that's 1 times 4e to the 2t. And lastly, let's do 1, 2. So it'll be a 1, 2e to the 2t, 2e to the t, minus 0, 2e to the t. So I get r prime cross r double prime is 8 minus 4 is 4e to the 3t. You have 8e to the 3t minus 4e to the 3t is 4e to the 3t. I have 0 minus 4e to the 2t, and I have 2e to the 2t. Okay. So let's find the length of this. So the norm of r prime cross r double prime is 4e to the 3t squared plus negative 4e to the 2t squared plus, oh, those are the same, plus 2e to the 2t squared. And so this is equal to 16 e to the 16 plus 16e to the 4t plus 4e to the 4t. Combine like terms. I get 16 oh wait, oh, look at that. That's an e to the t. Uh-oh. Ooh, that's an e to the t. That's an e to the t. That's an e to the 2t. Oh, okay, so that is, let's factor out 4e to the 4e to the 2t. So what it means is 4e to the 4t plus 4e to the 2t plus 1. Ooh, that make a big difference. So this, the norm of r prime cross r double squared is 4e to the 2t, and this is a 2e to the 2t plus 1 squared. Okay, and so r prime cross r double prime is 2e to the t times 2e to the 2t plus 1. Again, everything here is positive, so I don't have to worry about absolute values. And so the tangential component is the norm of r prime dot r double prime over the norm of r prime. So if I do that, the dot product and divide by that. So that was a 4e to the 2t over 1 plus. Okay, so let's do that. So it was 4e to 2t, 1 plus 2e to 2t, and 1 plus 2e to 2t. So this was 4e to the 2t times 1 plus 2e to the 2t divided by 1 plus 2e to the 2t. So those cancel. And so I get that A, the tangential component of the acceleration, is 4e to the 2t. And I get that the normal component is r prime cross r double prime, the norm of that, divided by the norm of r prime. Okay, so that was 2. Oh, so it's almost the same thing, except there's a 2 there. So this is equal to stop. So the normal component is 2e to the 2t. It was 2e to the 2t plus 1, and this was 1 plus 2e to the 2t. Okay. And so these cancel. Okay, so these cancel. And so I get that the normal component of the acceleration why am I saying it is a vector? Because it's not a vector. Okay, that was just an error. Okay, this is a typo. So the normal component is just 2e to the 2t. And that is my answer. Okay, so let's do, as a last example, determine the radius of the event horizon of a black hole. This what's called the Schwarzschild radius. Let's see, denote the speed of light. At the event horizon of a black hole, the escape velocity is c, the speed of light. So we're going to be doing this using Newtonian mechanics. Of course, you should be using, general relativity, but we're going to show that even with physics, assuming that the speed of light is finite, it can still get the same results. So use Newtonian physics and assume the speed of light is finite, we'll get a lot of the results of general relativity. Let's do this. So first off, the energy, well, energy is just kinetic energy plus potential energy. So by the conservation of energy, the initial energy must equal the final energy. Well, letting the distance go to infinity, we have that both the kinetic energy and potential energy goes to zero. Therefore, the initial energy of your system must be zero. And so the initial kinetic energy must equal the initial potential energy. And so the kinetic energy is just 1/2 mv squared. The potential energy, well, let's just assume, so this is 1/2 mv squared. Assume that the only force that matters is gravity. So we're going to assume that in this case, gravity rules everything. And so the only potential energy will be gravity. So we're assuming that this is a nice black hole. It doesn't have any other forces. So there are no tidal forces. It doesn't have, all this, any electrical charge or anything else. It's just the only force on it will be gravity, which in many instances, this will give you a very good model. And so the potential energy, just gravity, so Gm m over r. Okay, so let's say that that's zero. M, little m, is your mass, and big M is the mass of your black hole. So the m's cancel, the m's cancel. Let's multiply by 2r. Just to make everything look a little nicer. So the 2's cancel, so you get an r. And let me assume here that the escape velocity is c. So let's let that equal c. And so I have that r squared, that r, there's only one r, that r, v squared, c squared, minus the r's cancel, 2gm is equal to 0. Okay. And so trying to get control back of the screen. Okay, good. My screen. I can control my screen again. Okay, so let's solve this for r. And so I get that r is equal to 2gm over c squared. And that is the radius necessary for you to have a black hole. And so if you have that as your radius of your object of this particular mass, then nothing will be able to escape. Then the escape velocity of any object will be the speed of light. And so we call that, well, a black hole if the escape velocity is the speed of light. Let me just do Small little calculation. So suppose, well, approximately, so Newton's universal gravity constant is approximately 6.67 times 10 to the negative 11 Newton meters per kilogram squared. The speed of light is approximately 2.99 times 10 to the 8 meters per second. And for the Earth, the mass of the Earth is approximately 6 times 10 to the 24 kilograms. And so if you crush the Earth so that it had a radius of 8.9 millimeters, approximately 1 centimeter, then it would become a black hole. So that's it for today. So we made a black hole today. Let's finish that off. Okay, and then stop this recording.